Bismillahirrahmanirrahim. Welcome back with lecture 6 in discrete structures. In this lecture, previous lecture summary, here we were studied about why study set theory, sets, operations on sets, membership documentation, Venn diagram, and in this lecture we will discuss about the introductions to set theory 2. Uh, we will first discuss about the outlines of this in the next slide. If we discuss about the outlines of today's lecture, so it's the procedural variants, properties of sets, empty set properties, difference properties, set identities, Boolean algebra, and set theory puzzles. The procedural variants of the set definitions. Let X and Y be subsets of a universal set U, and suppose X and Y are elements of U. X, which is X belongs to the X belongs to X union Y if and only if X belongs to X or X belongs to Y. If the second property X belongs to X intersection Y, it implies X belongs to X and X belongs to Y. If X belongs to X minus Y, difference of X, Y, if and only when X belongs to X and X doesn't belongs to Y. And if X belongs to the set X, it means X doesn't mean to the X dash X complement. You can write XC. If XY belongs to X cross Y, the binary operations, then it means X belongs to X and Y belongs to Y. So these are the procedural variants of the set definitions. We will discuss about the properties of the sets. There are some theorems. Inclusion of intersection for all sets A and B. A intersection B is a subset of A, and A intersection B is a subset of B. This B is only for the part of this. You can ignore this B. Inclusion in union for all sets A and B. A is subset of A union B, and B is the subset of A union B. This B can also be ignored. This is only for the part. Transitive property of subsets for all sets if A, B, and C. If A is a subset of B and B is a subset of C, then you can say that A is a subset of C. So A is the subset of C. So this is the transitive property of subsets. Now we give the proofs of all these theorems. For all sets A and B, A intersection B is the subset of A. Now we suppose that X is an element in A intersection B. It means that X is in A and X is in B. This allows you to complete the proof by deducing that in particular X is in A as was to be shown. Now there is note that this discussion is just a special case of valid argument form. If P and Q and since P, similarly we will done with others. Here we present the set identities. Let all sets refer to below be subsets of universal set U. First is the commutative laws. For all sets A and B, A union B is equal to B union A, and A intersection B is equal to B intersection A. You can write in logics as P or Q is equal to Q or P. Equivalent. Here you used equivalent. Associative laws also holds for all sets A, B and C. A union B union C is equal to A union B union C, and we will discuss about with respect to the intersection A intersection B intersection C is equal to A intersection B intersection C. Now we present the distributive laws for all sets A, B and C. A union B intersection C is equal to A union B intersection A union C. And the second part of this distributive laws, A intersection B union C is equal to A intersection B union A intersection C. So this is the commutative law with respect to intersection and union. Here we present, next we present the identity laws for all sets A union phi is equal to A. If we take the union of any set with the empty set, then the answer will be that set. And if we take intersection of any set A with the universal set, then it's also A. Now we present the complement laws. A union A complement is equal to U. If we take the union of A and A complement, then it's equal to the universal set U. And in B, if we take intersection of A with the complement A dash, then it's the empty set. Double complement law. For all sets A, A A complement, if we take the complement of A with A, then it becomes the original set A. Idempotent clause. For all sets A union A is equal to A, and A intersection A is equal to A. If we take the intersection with itself, then the answer is itself. And if we take the union of itself, then it's also the universal bound laws. For all sets A union universal set U is equal to the U. And if we take the A intersection phi, then it's phi. De Morgan's laws. For all sets A and B, A union B complement is equal to A complement intersection B complement, and in second part A union A intersection B complement is equal to A complement union B complement. So this is for part B. This so you can ignore this B. Absorption laws. For all sets A and B, A union A intersection B is equal to A, and A intersection A union B is equal to A. So this is the absorption laws. Complements of universal and the empty set phi. The complement of the universal set U is the empty set, and if we take the complement of the empty set, then it's U, the universal. Now we discuss about the set difference law. For all sets A and B, A difference B is equal to A intersection B complement. So these are the laws for sets. Now a distributive laws for sets. So for all sets A union B intersection C is equal to A union B intersection A union C. We prove this. Suppose A and B are the sets, we have to show A union B intersection C is a subset of A union B intersection A union C. First we show the left hand side is the subset of the right hand side, and then we show the right hand side is a subset of left hand side. So if both sides are subsets of each other, then the result is that both sides are same. Let's suppose X belongs to A union B intersection C. Then by definition of union, X belongs to A or X belongs to B intersection C. It means X belongs to A or X belongs to B intersection C. So we take let case x1, case 1, X belongs to A. If we take this X belongs to A, since X belongs to A, then X belongs to A union B. So it's the definition of the union, and also X belongs to A union C. So if X belongs to A, then X also belongs to A union C. For any union which is taken with A, X belongs to that union. So it's also the definition of union. Hence X belongs to A union B and A union C. It is the definition of intersection. But from this statement we can say that if X belongs to A union B and X belongs to A union C, it means that X belongs to A union B and intersection we use instead of and intersection A union C. It's the definition of intersection. Now we take the second case. X belongs to B intersection C. Since X belongs to B intersection C, it means then X belongs to B and X belongs to C. It's a definition of intersection. Since X belongs to B and X belongs to A union B, and since X belongs to C, then X belongs to A union C. So this is the definition of union. Hence X belongs to A union B intersection A union C. It is the definition of intersection. In both the cases, X belongs to A union B and A union C in both cases. So we can say that the left hand side from which we take X, it also belongs to the right hand side. So the left hand side is the subset of the right hand side. Now we have to show that the right hand side is the subset of left hand side. A union B intersection A union C is the subset of A union B intersection C. We suppose that X belongs to A union B intersection A union C. Left hand side we take. We have to show here that X belongs to right hand side. Then we will say that it's the subset of this side. By definition of intersection, X belongs to A union B and X belongs to A union C. Consider the two cases, X belongs to A and X doesn't belong to A. For the case 1, if we take X belongs to A, since X belongs to A, so we can immediately conclude that X belongs to A union B intersection C. So it's a definition of union. And if X doesn't belong to A, it means since X belongs to A union B, so X is an at least if any element which is from union, so this element must be at least in one of A or B. So X is in at least one of this A and B. But X is not in A. We say that hence X is in B. Here we take X doesn't belong to A. Hence X is in B. Similarly, since X belongs to A union C, so X is in at least one of A or C. But X is not in A, so X is in C. We have shown that in both X belongs to B and X belongs to C. So by definition of the intersection, X belongs to B intersection C. So it follows the definition of union that X belongs to A union B intersection C. In both the cases, A union B intersection C is the subset of A union B intersection C. So from these two equations, you can see that A union B intersection C is equal to the right hand side A union B intersection A union C. So left hand side is equal to the right hand side. Now we prove the De Morgan's laws for the sets. Prove that for all sets A and B, A union B complement is equal to A complement intersection B complement. Similarly, as in the previous slide, we proved the left hand side is equal to the right hand side by showing that left hand side is subset of right hand side and right hand side is a subset of left hand side. Then we can say that both sides are equal. Similarly, here we will show suppose X belongs to A union B complement. It means X doesn't belong to A union B. If the element which belongs to the complement, then that element doesn't belong to the original. But to say that X doesn't belong to A union B, it means that it's false. That X is in A or X is in B. It means X is neither in A neither in B. But in Morgan's laws of logic, this implies that X is not in A and X is not in B. So which we can write X doesn't belong to A and X doesn't belong to B. Hence X belongs to A complement and X belongs to B complement. If the element doesn't belong to that set A, then it belongs to the complement of that set. So it's a definition of complement. It follows that by definition of intersection that X belongs to A complement intersection B complement. So A union B complement is a subset of A complement intersection B complement. So this is the we show that the left hand side is a subset of the right hand side. Similarly, now we prove that right hand side is a subset of left hand side. Suppose X belongs to A complement intersection B complement. X belongs to A complement and X belongs to B complement. And by definition of the complement, X doesn't belongs to A and not belongs to B. In other words, we can say that X is not in A and X is not in B. By De Morgan's laws of logic, this implies that this is false, that X is in A or X is in B. which can be written X doesn't belong to A union B. It's a definition of union. Hence, by definition of the complement, X belongs to A union B complement. It follows that A complement intersection B complement is a subset of A union B complement. So this is the definition of subset. If both are the subsets of each other, then it means that both sides are equal. The empty set. If E is a set with no elements and A is any set, then E subset of A. We suppose that X, we suppose not, X doesn't belong to A. Suppose that there is a set E with no elements and a set A such that E in A, then there would be an element of E that is not an element of A, but there can be no such elements since E has no elements. So it's a contradiction which produces here. Hence, the supposition that there are sets E and A where E has no elements is false, and so the statement of the theorem is proved true. Now we show that the uniqueness of the empty sets. So there is only one set with no elements. In other words, we can say that E1, E2, if are two non-empty empty sets, then E1 is equal to E2. Suppose that E1, E2 are both sets with no elements, so E1 is subset of E2. Since E1 has no elements, so since E2 has no elements, thus E1 is equal to E2. So this is the definition of set equality. A set with no elements is a subset of every set. Now we prove this. So if E is a set with no elements and A is any set, then E is a subset of A. Suppose that there exists a set E with no elements and a set A such that X doesn't belong to A, then there would be an element of E would be an E, then there is no element of A in E. So it can be no such element since has no elements. So it's a contradiction. So we can see that a set with no elements is a subset of every set. A proof or conditional statements we give here proof that for all sets A, B and C, if A is subset of B and B is if A is subset of B and B subset of C, then A intersection C is equal to the empty set. So we suppose that it may be, you can say that it is Q of X and this is P of X. Suppose there is an element X in A intersection C. So by definition of the intersection, X belongs to A and X belongs to C. Then since A is a subset of B, X belongs to B, so it's the definition of subset. If since B is subset of C complement, then X belongs to the C complement. So it is also again the definition of subset. So it follows that the definition of the complement that X doesn't belong to C, thus X belongs to C and X belongs to C, which is a contradiction. If we say X belongs to C and then we say X doesn't belong to C, it means it's a contradiction. So X in A intersection C is a false, and thus A intersection C is the empty set or phi. Now we will discuss here about the finding a counter example. For all sets, counterexample for an entry is for all sets A, B and C, A minus B union B minus C is not equal to A minus C. Here is not equal. Please correct it. Let A is equal to 1, 2, 3, 4 and B is equal to 2, 3, 5, 6 and C is equal to 4, 5, 6, 7. And C is 4, 5, 6, 7. Then A minus B is equal to 1 4. You can see from these two sets A minus B. So this is 1 and 4. These are the elements which are not in B. So the difference of A, B is 1 4. And B minus C, B difference C, you can see that it's 2, 3. The elements in which are in B and not in C. And if we take A difference C, then it's 1 2. You can easily find out from this. Hence A difference B union B difference C is equal to, we can say 1 4 union 2 3. So it's when we take the union, then it's 1 2 3 4, whereas A minus C is equal to 1 2. Here A minus C is equal to 1 2. So which is not equal to this. So we have showed that A minus B union B minus C is not equal to A minus C. Another example is represented here. Let A is equal to 5 and B is equal to 3 and C is equal to 5. Then A minus B difference B is equal to 5. So you can these you can see this example. Let if we take A minus C, which is also 5, hence A minus B union B minus C, it's 5 union 3, which is 3, whereas A minus C is equal to 5. So we have that A minus B union B minus C is not equal to A minus C. So here deriving a set difference property, we construct an algebraic proof for all for the proof that for all sets A and B and C, A union B minus C is equal to A minus C union B minus C. Let ABC be any sets, then by the definition of set difference law, A union B minus C, difference C, you can say minus C also, is equal to A union B intersection C complement. So which is equal to A union B intersection C complement. By now we use by the commutative law for intersection C complement intersection A union B. So we take C intersection with A union C intersection with B with union. This is a distributive law. So by the commutative law for intersection, you can say that A intersection C complement A, C complement intersection A is equal to A complement A intersection C complement union this. You can also use commutative law on this one. So this will become B intersection C. So it's now we use the set difference laws. A intersection C complement means A minus C union B minus C. Construct an algebraic proof for that for all sets A and B. A minus A intersection B is equal to A minus B, or maybe A difference B. We suppose A and B are unit sets, then A minus A intersection B is equal to A intersection A intersection B complement. This is so by difference by the set difference law, A intersection A complement union B complement, it's by De Morgan's laws. So this we can use here the distributive law, A intersection A complement union A intersection B complement. This is the distributive law. Now by the complement law, A intersection A complement is equal to phi union A intersection B complement. A intersection B complement union phi. So this is the commutative law for U. You can use here the commutative law. So by the identity law, union of any empty sets with the set is the answer will be that set. So this will gives A intersection B complement. So it's equal to A minus B. This is the set difference law. Same is it's the right hand side of the proof. Boolean algebra and set theory, logical equivalences and set properties are discussed here in this slide. For all statements P, Q, and R, P or Q, which is equivalent to Q or P, commutative law in the logical equivalences, similar for all sets A, B, and C. A union B is equal to B union A. And similarly for the intersection, for intersection P and Q is equivalent to Q and P. Similarly for the in the sets A intersection B is equal to B intersection A. And if we discuss about the associative property P and Q and R, which is equivalent to P and Q and R. So for sets A union B union C equivalent to A union B union C, and similarly for intersection. And if we discuss about P distributive law, P and Q or R, which is equivalent to P and Q or P and R. So it's A intersection B union C, which is equivalent to A intersection B union A intersection C. Similarly for the second distributive law, and for P or C, which is equivalent to P. Similarly for A union phi is equal to A. And for tautology, P intersection T, which is equivalent to the P. So A intersection U with the universal set is equal to A. And P or negation Q, which is equivalent to T. So in sets A union A complement, it's equal to U. And P and negation P, which is equivalent to C. So in sets A intersection A complement is equal to phi. So this is the relevancy between the logical equivalences and the sets intersection and union. Negation and negation P, which is equivalent to P, then in sets A complement whole complement is equal to P or P, which is equivalent to P. So A union A is equal to A. And P and P, which is equivalent to P, and in the sets you can say A intersection A is equal to A. And for P or T, which is equivalent to T, in sets A union, the universal set U is equal to U. And similarly for the C, P intersections P and C is equivalent to C. So in sets P intersection phi is equal to phi. So for negation P or Q, it's equivalent to negation P and negation Q. So A union B complement is equal to A complement intersection B complement. And if negation of P and Q, which is equivalent to negation P or negation Q, so this in sets A intersection B complement is equal to A complement union P complement. And similarly for the distributive law for same P or P and Q is equivalent to P, A union A intersection B is equivalent to. Similarly for the second distributive law, and for the negative tautology, which is equal to C, so uni uh, complement of complement of and for negative C, negation C, which is equivalent to T, so phi, the component of phi is equal to U. Here is the Barber puzzle. You can read it. It may be questions for you that in a certain town there is a male barber who shaves all those men and only those men who don't shave themselves. So does the question shave the barber? Does the barber shave himself? Neither yes or no. You can read the solution in this slide. So the previous half lecture summary which I have discussed with you people is procedural versions, properties of sets, empty sets and difference properties, set identities, Boolean algebra and set theory. Now we discuss about the relations, about the functions. In this topic we will discuss about the basic concepts of relations, types of relations, relation on a set, the inverse of a relation, representing relations using diagrams, NRY relations. What's relations? We start it with an example. Let P be a set of a set of people. C be a set of scores, and R be the set of relation describing which person drives which cause. Let P be the set of persons Corley, Susanne, Peter, Carla, and C is the set of cars Mercedes, BMW, tricycle. R is a set of relations. We can say that Corley, Mercedes, Susanna, Mercedes, Susanna, BMW, Peter, tricycle. This means that the car drives a Mercedes, Susanna drives a Mercedes and a BMW, Peter drives tricycles. And it also means that Corley does not drive any of these vehicles. If we want to describe a relationship between elements of two sets A and B, we can use ordered pairs with the first element taken from A and the second element taken from B. Since this is a relation between two sets, so it's called a binary relation. Uh, we give an example at A and B, which is sets. A binary relation R from A to B is a subset of A cross B. In other words, for a binary relation R, we have R which is a subset of A cross B. So we use the notations A R B, which means A relation B. And if we write A R dash B, it means it denotes that A B doesn't belongs to R. If we have two sets A 1 2 3 4 5 and B is 5 6 7 8 9. The Cartesian product of A and B is, we have already discussed, 1 with each element of B, 1 5 1 6 1 7 1 8 1 9. And for the second element B of A, 2 with each element of B, 2 5 2 6 2 7. And similarly for the uh, third element 3 with each element of B, 5 6 7 8 3 5 3 6 3 7 3 8. So the rule is to add 4, a relation R 1 5 2 6 3 4 4 8 5 8. So we take these relations from this Cartesian product. So R is a subset of A cross B. One-to-one relations. This is an example for one-to-one relation. If we take 1 with 5, the rule is add 4, and 2 with 6, 3 with 7, 4 with 8, 5 with 9. It means that 1 is the output, input, and second is output, and that output is only for that element, not for any other element. Many to many relations. If we have two sets, for example, A is Ahmed, Peter, Ali, Javeria, Hamad, and B is Paris, London, Dubai, New York, Cyprus. The Cartesian product of A and B is, which have we already discussed, Ahmed with Paris, London, Dubai, New York, and Cyprus. Similarly, for uh, Hamad, and similarly for Peter, for each city, Paris, London, Dubai, similarly for Ali, similarly for Javeria, and similarly for Hamad. The last in element in the ordered pair in the Cartesian product is Hamad, Cyprus. The rule is has invited. R with the relation which is a subset of A cross B. So this is R Ahmed Paris, Ahmed Dubai, Peter London, Peter New York, Peter Cyprus, Javiria Paris, Javiria Cyprus, Hamad Dubai, Hamad Cyprus. So R is a subset of I cross B. So many to many relations in, if we display it in diagram. So Ahmed has visited Dubai, Ahmed has visited Paris. Peter visited London, Peter visited New York, Peter visited Cyprus. Similarly, for Chaviria, which he has visited Paris, has visited Cyprus. And for Hamad, Hamad visited Dubai and Cyprus. So there are many arrows from each person to each city. So uh, this is the example of many to many relations. In if we have two sets, same, uh, which I this slide I have already discussed with you people in, so it's repeated. Many to one relation. If a person, rule is R has a mass of kg. This set is for kg. Bilal has a mass of 62 kg. Many to one relation, and Peter also has a mass of 62. Salma has also mass of 62 kg. So it shows that three peoples have the same mass. So it's the many to one relation, and this shows Alia has a mass of 66 kg, George, which has 64, Aziz has 64 kg. This is many to one relation. In this case, each person has only one mesh, yet several persons have the same meshes. One-to-many relations. If we take set A, which is length in centimeters, and set B is a set of objects in which pen, pencil, ruler, needle, stick are the elements, and if the length are 14 and 13 centimeter. Pen has 14 centimeter length and 14 centimeter length of also pencil, so it's one to many relations. So these are the relations which we discussed in this. This is the uh, many to one relationship, one to one relationship. This shows one to many relationships, and this one shows for many to many relationships. A relation on the set A is a relation from A to A, which R shows from A to A. In other words, a relation on a set A is a subset of A cross A. It's a subset of itself, the Cartesian product of itself. Here is the example at A is equal to 1, 2, 3, 4, which ordered pairs are in the relationship R. A, B, the ordered pair such that A is less than B. We make all the ordered pairs in which A is less than B. So 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. We can't make 2, 1. We can't make 2, 3, 1, because if we make ordered pair 3, 1, uh, I write here 3, 1. This is an also an ordered pair of you can say, but in this condition doesn't hold that A is greater than B. So we take all the ordered pairs in which A is less than B. So this is the graphical view of that example. One in 1 2, 1 is less than 2, 1 3, 1 less than 3. These are the all the ordered pairs in which A is less than B. So we take all 1 2, 1 3, 1 4, 2 3, 2 4, 3 4. This shows we can't make 2 1 3 1. So this is against the condition. How many different relations can we define on a set A within n elements? A relation on a set A is a subset of A cross A. Uh, how many elements are in A cross A? So they are n square. There are n square elements in A cross A. So how many subsets relations does A cross A have? So the answer we can define here 2 raised to the power n. Relations on an infinite set, the less than relation for real number. Define a relation L from R to R as follows for all real numbers x and y, such that x relation to y if and only if x is less than y. Is this relation 53 relation to 57 relation to 53? It's no, because 57 is not less than 53. This is true because minus 17 is less than minus 14. So Uh, if we describe this in a graphical view, the less relation for real numbers may be shown as this figure. Relations on an infinite set. The congruous modulo 2 relation. If we define a relation E from Z to Z as follows: for all M n belongs to Z cross C, M with E, M relation with E to n if and only if m minus n is odd, even. Is 4 equal to 0? Because 4 minus 0 is equal to 4, so this is even, it's true. And if we take 5 with the relation 2, so 5 minus 3 is equal to 2, which is odd, so it's false. The congruous modulo 2 relation, we may define a relation E from Z to Z as follows. For all Mn ordered pairs belongs to Z cross Z, that M minus N is even. So there are many such lists. One is this, which shown in this example. The congruous modulo 2 relation, we define a relation from Z to Z as follows. For all Mn which belongs to the binary operation Z cross Z, M within relation with N if and only if M minus N is or even. Here we prove that if N is an odd integer, then N is with the relation 1, N minus 1 is equivalent to this. Suppose n is an odd integer, then n is equal to 2k power plus 1. For some integer k, now by definition of the relation, n with relation with 1 if and only if n minus 1 is even. But by substitution, n minus 1 is equal to 2k plus 1 minus 1, which is equal to 2k. And since k is an odd integer, so 2k is 0. A relation on a power set, let x is equal to abc, and power of x, power set of this x is all these elements are these sets are the power sets. Phi is the element of every power set, and the set x is also the power set of itself. A, B, C, A, B, A, C, B, C, A, B, C. These are all in elements in power set. We define relation S from power set to Z as follows. For all sets A and B in power set, as A is either in relation B, if and only if A has at least as many elements as B. So is AB is in with relation with BC? So yes, because there are two elements, and which is 2 is greater or equal to 2. The inverse of a relation. And now we discuss here about the inverse. If R is a relation from A to B, then a relation R inverse from B to A can be defined by interchanging the elements of all the ordered pairs. You can say that the input becomes the output and output becomes the input. Let R be a relation from A to B, define the inverse relation. So R inverse is equal to Yx belongs to B cross A, such that Xy belongs to R. The inverse of a finite relation, let A is equal to 2, 3, 4 and B be the set 2, 6, 8, and let R be the divides the relation from A to B. For all xy belongs to A cross B, x is in with relation with y if and only if x divides y, y divides x. We make here R and R inverse. R if 2 and 2, you can say we replace the places of all these. 2, 6 here in R inverse 6, 2. If this is 2, 8, this will become 8, 2. The inverse of a finite relation, we take A and B are two sets. So if R is this and R inverse are this, then by a diagram we can show all the relations are with R, and this which shows the relations of R inverse. R inverse are have these ordered pairs. So if B is this and A is this, so R inverse goes from B to A. If R goes from A to B, then R inverse goes from B to A. For all xy belongs to R cross R, x is in relation with y if and only if x is equal to 2x mod. We here draw the cross of R and R inverse in the Cartesian plane. This will x and this will y. Then x, we defined here the relation y is equal to 2x mod. This is the absolute value of x, and in R inverse, so it's will become y is equal to 2x mod x. Here is xy and here is yx. So this is the first coordinate and these are the second coordinates. So in R inverse, so you can see that second coordinates will becomes first coordinate and the first coordinate becomes the second coordinate. Here we define by in Cartesian plane R, we draw the graphs of R and R inverse. This is the graph of R and this is the graph of R inverse. Representing a relation using digraphs. So here we have a definition: a directed graph or digraph consists of a set V of vertices or nodes together with a set E of ordered pairs of elements of V called edges or arcs. The vertex A is called the initial vertex of the edge AB and the vertex B is called the terminal vertex of the B. So we can use arrows to display the graphs. So these are the arrows used here. We display the digraph with V A B C D and E which has a binary relations, ordered pairs A B A D A B B B D C A C B and C B. So this is with A C C A A B and this with A D. This shows this line shows A B and this line shows B D. If we B B, this shows B B itself. And H on the form BB is called a loop. It may call a loop. If we have a set A and define a relation R on as follows. Uh, for all xy belongs to A, x with relation with y if and only if 2 x minus y is divisible by 2. We draw the graph of this. You can see this example. Here we draw the directed graph of R from this example. NRA relations or binary relation is a subset of Cartesian product of two sets. Similarly, an array relation is a subset of Cartesian products of n sets. Here we given a sets n, a1, a2 up to an, and n array relations are on a1 by a2 by up to an is a subset of a1 into a2 an. The special cases of 2 array and 3 array and 4 array relations are called binary, ternary, quaternary relations respectively. The sets a1, a2, a3 uh, are called the domains and relations, and n is called its degree. So these are the examples of NR relations. If let R is equal to this, where A, B, C are the divisible by A, which is equal to B, and B is equal to 2C with A, B, C belongs to N. So what's the degree and degree of R? So what are its domains? Its domains are all equal to the set of integers. Is 2 for 8 in R? No. Is 2 for 1 in R? Yes. These are in R. A simple database application. Consider a database of students whose records are represented as 4 tuples with the fields student name, ID number, major, and GPA. So R uh, which shows we can make with these relations that represent data bits. These are from tables, and since they are often displayed as table. So this is a lecture summary which we discussed in this lecture. Uh, Basic concepts of relations, types of relations, relations on subsets, the inverse of relation, representing relations, and NRY relations. So thanks for this video, and we will meet inshallah with the next lecture in lecture 7.